Okay, let's dive in. Quantum mechanics QM, it's the bedrock of modern physics, describing the microworld with just incredible accuracy.
It really is. But that success, it came with some really heavy philosophical questions attached.
Right, like, has QM actually undermined things we took for granted? Causality, objective reality, even the idea that you need a creator.
That's exactly the territory we're exploring. Our sources argue that a lot of the popular takes, the universe is random, it popped out of nothing, they might be built on interpretations that are, let's say, philosophically fragile.
And maybe scientifically incomplete, too.
Sometimes, yes, they often gloss over tricky spots within QM itself, like the whole measurement problem.
Okay, so our mission today, cut through that noise. We need to get clear on things like superposition, uncertainty, figure out what quantum causality really means.
And hopefully reveal the deep order that's actually there, even under the quantum weirdness.
Let's get into it. So before QM, we had classical physics.
Yeah.
Newton, Einstein. A universe that felt solid, right?
Very solid. Objective reality, clear cause and effect, laws that worked the same whether you were looking or not. Predictable, like clockwork.
And QM just smashed the clockwork.
Pretty much. The big change is particles aren't points with exact positions anymore. They're described by this thing called a wave function. See it there.
And that doesn't tell you where it is?
Nope. Only the probability of finding it somewhere if you look. It's a fundamental shift from certainty to, well, to odds.
Which brings us to superposition. This idea still feels mind-bending. A particle is in many states at once.
Like Schrödinger's famous cat, alive and dead. Or a particle taking multiple paths simultaneously in an experiment. It exists in a haze of possibilities.
Until you measure it.
Exactly. The moment of measurement, poof, the wave function collapses. It snaps into one single definite state, and that collapse. That's where the big philosophical fight started.
Okay, so you had two main camps, right? Let's start with the positivist view, the Copenhagen Interpretation. Bohr, Heisenberg, what was their take?
Their basic idea was, look, the wave function is just a calculation tool, a brilliant one, but it doesn't actually describe reality itself.
So reality isn't real until we measure it.
That's the radical part. Bohr famously said something like, there is no quantum world, there is only an abstract quantum physical description. Measurement doesn't just reveal reality in this view, it kind of creates it.
Hold on. If measurement creates reality,
Yeah.
what about everything we're not looking at right now? Does the moon cease to exist when nobody's observing it?
That's precisely the sort of thing that bothered Einstein immensely. Which brings us to the other side. Realism. Einstein, Penrose. And they insisted reality is objective. It's there whether we look or not.
That's where God does not play dice comes from.
Exactly. Einstein felt QM had to be incomplete because it relied on chance and couldn't describe what a particle was really doing before you measured it.
And this whole mess is the measurement problem.
Precisely. Penrose really hammered this home. He points out that standard QM is, well, inconsistent. You've got the Schrödinger equation describing this smooth, predictable evolution of the wave function.
Deterministic even.
Totally deterministic. But then, bam, measurement happens, and that smooth evolution just breaks. It jumps. An unpredictable quantum leap.
But wait, the detector, the measuring device, it's made of atoms too, isn't it? Why don't its atoms follow the same deterministic equation? Why the sudden change of rules?
That's the inconsistency Penrose flags. It feels arbitrary. His view is that collapse must be a real physical process happening objectively, maybe something to do with gravity at the quantum level, not just a quirk of observation or consciousness.
Okay, but if quantum stuff is so weird, existing in multiple states, why don't we see that in our everyday world? Why isn't my coffee cup simultaneously here and, I don't know, on Mars?
Great question. That brings in decoherence. It's basically the universe constantly measuring things.
How does that work?
Think about your coffee cup. It's constantly bumping into air molecules, photons are bouncing off it, interacting with its environment in countless ways.
Okay.
Each interaction acts like a tiny measurement, forcing the cup's wave function to collapse incredibly quickly. It gets locked into one definite classical state.
So the quantum weirdness gets washed out for large objects.
Exactly. The bigger the object, the faster decoherence happens. It suppresses the superposition and makes sure the macroscopic world behaves itself, looking solid and predictable like we expect.
Okay, let's talk causality. The big challenge people point to is Heisenberg's uncertainty principle. You can't know position and momentum perfectly at the same time.
Right.
And the conclusion often jumped to is, therefore, the universe is fundamentally chaotic, random, no cause and effect.
Yeah, that's a common misunderstanding. We need to be careful here. The uncertainty isn't just because our tools are clumsy, it seems to be baked into the nature of quantum things themselves.
The fundamental limit.
Yes. And this is crucial just because we can't predict the single outcome of one measurement, like exactly where one electron will hit a screen.
Hmm.
That doesn't mean causality is gone. It's just different.
How so? If the outcome is random, where's the cause?
You have to look at the evolution before the measurement, the Schrödinger equation, remember, the one that describes how the wave function changes over time.
The deterministic one.
The fully deterministic one, it perfectly connects the quantum state now to the quantum state in the future. That mathematical evolution is a form of causality. It dictates how the probabilities change.
Ah, okay. So causality isn't about predicting one specific outcome anymore.
Exactly. It's about predicting the range of possible outcomes and their precise probabilities.
Stephen Hawking called it a new kind of determinism.
He did. Nature determines the set of possibilities, and crucially, the distribution of those possibilities over many events is statistically determined. It's predictable.
So fire a million electrons.
Yeah.
You can't predict where any single one lands, but you can predict the overall pattern they'll form.
Precisely. The randomness of the individual gets averaged out by the law of large numbers, revealing an underlying causal order in the statistics.
Okay, that makes sense. But what about entanglement? That spooky action at a distance. Two particles linked, influencing each other instantly across space. Doesn't that break causality? Seems like faster than light influence.
It definitely challenges local realism, the idea that influences can only travel locally, no faster than light. It's spooky.
But not causality breaking.
Correct. According to our sources and the standard understanding, it doesn't violate causality because of something called the no signaling principle.
Meaning?
Meaning you can't actually use that instantaneous correlation to send a message faster than light. Measuring particle A instantly affects the probability of particle B's state, but you can't control which state A collapses into to deliberately send, say, a Morse code message to B.
So information transfer is still limited by the speed of light.
Exactly. The cosmic speed limit holds. Causality, in that fundamental sense, remains intact.
Let's switch gears to cosmology. QM often gets pulled into arguments about the universe's origin, right?
Ooh.
The idea it just popped out of nothing via quantum fluctuations.
Yes, you hear that a lot, often associated with thinkers like Lawrence Krauss or Stephen Hawking in certain contexts. Universe from nothing, no cause needed.
But the sources we looked at are very critical of this specific claim.
Extremely critical. And the core issue is a definitional one. What do they mean by nothing?
Isn't nothing, the absence of everything.
That's philosophical nothingness. But the nothing they invoke in these quantum creation models, the quantum vacuum, is very far from that. It's absolutely not nothing.
Okay, unpack that. What is the quantum vacuum then?
Well, for starters, it has energy. 0-point energy.
Yeah.
It's fizzing with virtual particles popping in and out of existence. It has quantum fields permeating it. It has structure.
And crucially,
It's governed by physical laws.
Yeah.
The very laws of quantum mechanics that supposedly allow the fluctuation to happen in the first place.
So to call this energy-filled, structured, law-governed system nothing.
It's a category error, as the sources put it. It's confusing a highly complex physical system with the philosophical concept of non-being. It's a bit of a bait and switch, really.
And that leads to the next problem.
Yeah.
You need the laws before the universe can fluctuate into existence using those laws.
Exactly. Any model based on quantum tunneling or fluctuations presupposes the existence of incredibly complex mathematical laws like the Wheeler-DeWitt equation in some models, plus the whole framework of quantum field theory.
Where did those laws come from?
That's the question these models don't and perhaps can't answer. Laws can't just float in absolute nothingness, waiting to be instantiated, and laws certainly can't create themselves.
John Polkinghorne had a great analogy for this, didn't he?
He did, a really sharp one. He said something like, saying the universe emerged from nothing based on physics is like saying arithmetic created the numbers.
Meaning the laws described, they don't create.
Precisely. Scientific laws are descriptions of how reality behaves once it exists. They don't have agency or power to initiate existence. They aren't prescriptive, they're descriptive.
What about the idea that the universe's total energy is zero? Positive energy of matter balanced by negative gravitational energy, so it could emerge without violating energy conservation.
That's another common argument. But first, it relies on some pretty big assumptions about the universe's overall shape, often needing it to be perfectly closed, which isn't confirmed.
And even if the math worked out to zero,
it still doesn't solve the origin problem. Okay, the net energy is zero, maybe. But where did the positive energy and the negative energy that needed balancing come from in the first place?
And where did the laws governing energy and gravity, the ones doing the balancing act, originate?
Exactly. You're still left needing pre-existing laws and the initial stuff, even if it sums to zero, for the equation to even make sense. The ultimate origin remains unexplained.
So we've talked about the indeterminacy, the probabilities, the apparent randomness at the quantum level.
Uh-huh.
But then you look at the universe. It's incredibly ordered, structured, complex, galaxies, stars, life. How do those two pictures fit together? It feels paradoxical.
It does seem like a paradox, but maybe it dissolves when you look closer at the foundations of that quantum world. It's not pure chaos. It's governed by incredibly precise laws and constants.
Like Planck's constant H.
Exactly. Our sources call H something like the factory setting of the universe. It's this fundamental number that dictates the size of those quantum jumps, the granularity of energy and action.
And how finely tuned is this factory setting? If you tweak that dial just a tiny bit,
The consequences would be catastrophic. It's astonishingly sensitive. Let's say you increased H just slightly, maybe by, I don't know, 0.1%.
what happens?
Atoms basically fall apart. Electrons wouldn't be held as tightly. They'd escape their orbits easily. Stable atoms, complex molecules, chemistry as we know it, gone. No possibility of life.
Wow. And if you nudged it the other way, made slightly smaller.
Then atoms become too rigid, too stable. Electrons wouldn't be able to make the necessary jumps between energy levels easily.
Which means
Chemical reactions would grind to a halt. No bonding, no dynamic chemistry. The universe would be frozen, inert, lifeless in a different way.
And H affects more than just atomic stability, right? You mentioned it governs processes inside stars, too.
Yes, things like nuclear fusion rely on quantum tunneling particles overcoming energy barriers they classically couldn't. The rate of that tunneling depends directly on H.
So change H, and you change how stars burn, how long they live, whether they create the heavier elements needed for planets and life.
Precisely. It ripples through everything. The consistent conclusion from the sources is that this level of extreme precision, this fine-tuning, it points away from meaningless randomness towards what they describe as deep cosmic design, a system calibrated with unbelievable accuracy. Hashtag tag outro.
This has been really illuminating. We've seen that quantum mechanics, for all its predictive power, still has conceptual knots, like the measurement problem. It's not a complete picture yet.
Definitely incomplete in some ways. But what it does show, particularly with the deterministic evolution of the wavefunction and the precision of constants like H, is that the universe is profoundly structured. Causality isn't gone, it's just probabilistic at the quantum level.
And we also got clarity on why the quantum weirdness stays hidden from our everyday view.
Right. Decoherence and the law of large numbers effectively smooth things out, ensuring the macroscopic world we live in is stable and follows predictable, classical-like rules. The quantum effects are suppressed at our scale.
Which circles us back to the biggest questions. If cosmology points to a beginning for the universe, the Big Bang, and if those very laws governing that universe, like Planck's constant, show this incredible razor-sharp fine-tuning for complexity in life to exist,
Then you're pushed towards a pretty profound implication, aren't you?
what kind of entity or principle?
Something non-material, presumably volitional, existing outside of space-time and the physical laws themselves, must have been required to establish that initial state and calibrate those laws with such extraordinary precision.
That's the ultimate origin question.
It is, and it's a question that quantum mechanics, by revealing the universe's deep structure and its own limitations, forces us to confront, even though QM itself, as a scientific theory, can't provide the answer.